Good evening, everyone. Is it evening yet? Good afternoon, everyone, maybe. Welcome to the fifth and final press conference of today, which is on Cassini and Saturn, the 10th anniversary and new results. And taking part in this event, we have Nicola Zaltobelli, who is the ESA Cassini project scientist, and ESA is the European Space Agency. We have Luciano Yes, who is a Cassini team member from the Sapienza University of Rome in Italy. We have Athena Costenis, who is a Cassini co-investigator working at the Observatoire de Paris-Meudon in France. We have Stamatios Kremigis, who is another principal investigator of the Cassini's magnetospheric imaging instrument and head emeritus and principal staff at the Space Department of the Applied Physics Laboratory at Johns Hopkins University. And finally, we have Linda Spilker, who is the Cassini project scientist. And I'll hand over to our speakers. You can start, Nico.
Hello, good afternoon. So welcome to this press conference organized for the 10 years anniversary of the Cassini-Huygens mission, which has been in orbit around Saturn since 2004. And Cassini-Huygens is truly a milestone in the exploration of the outer solar system, as it has actually explored largely unknown territory where we had only first data from the Voyager spacecraft. And since then, Cassini-Huygens has provided a tremendous amount of data. And before we go into more details on the highlight of the science, I would like just that we step back and look actually at the beauty of this system revealed by the Cassini data. You see here on this picture, which is now iconic, the Saturn and all its rings seen from the Cassini point of view as the Sun is behind Saturn. And this picture has been taken last year in July. And I would like also to emphasize the fact that such an achievement in planetary exploration is only possible thanks to the international collaboration of the different space agencies and instruments nationally funded. And so in the early 80s, NASA, ESA, and the Italian Space Agency came together, teamed up around the concept that we are flying today. So in the second slide, you see a summary of the Cassini-Huygens mission timeline. It was launched in 1997. It arrived at Saturn in 2004. We had the prime mission starting with the landing of Huygens on Titan. And we had since then two extensions. In 2008, the mission was extended to catch actually the moment in time where the Sun is passing through the ring plane of Saturn, which is the Equinox mission. And the mission has been extended in 2010, a second time, the Solstice mission, until we reached in 2017 the Northern Solstice. So you see on this slide the position of Saturn during the Cassini mission, and you see that an important aspect of the mission is that we have covered half a period of, we will have covered nearly half a period of Saturn, and therefore half 2 seasons of the system. So we are able, through this extended mission, to see seasonal variations and all the phenomena related. So if I would summarize Cassini in a few numbers, this is 1 orbiter, 1 lander, 5 main science disciplines, and 18 instruments distributed on the orbiter and the lander. All of this picture actually tell a story by itself. We have, as the 5 disciplines, we have the icy satellites, symbolized in particular by the discovery of the cryovolcanic activity at Enceladus. Cassini explored the diversity and the rich dynamics of the rings. Cassini explored the magnetosphere of Saturn. You see here a view that will be explained in greater detail later on of the what is making the magnetosphere and how it works. The exploration of the Saturn atmosphere was also a big focus of the mission. You see here the northern polar vortex, which exists on the Saturn's north pole. And of course, one of the main story is the exploration of Titans. You see this series of images in the bottom from the Titan landing through to the determination of the interior structure of Titan. So if I focus a little bit on Titan, we could say that for the first time, actually, Cassini-Huygens lifted the Titan's veil. The picture of Titan before Cassini-Huygens was pretty homogeneous. You couldn't see much of the surface. And a first very interesting glimpse of how the surface looked like was given by Huygens during the landing. It was actually, and it is as of today, the man-made object that landed on the most remote object in the solar system. And during the descent, the surface became more and more interesting and complex. We saw these channels, which are a witness of fluvial activity, draining channels. And we touched down and we saw for the first time these pebbles on the surface made of very hard ice covered by organics. And we got also the first compositional analysis of the surface. So, and of course, Huygens was only a first step in discovering how Titan was made, because actually Cassini, the orbiter, can peer through the optically thick atmosphere with the radar wavelengths and with the near-infrared spectrometer. And you see here on the right the image, the map of the lake, which is being now made by the radar instrument. And you can see also this views of at near-infrared wavelengths at 5 microns of Titan, where we are now getting a full geological map of the surface. And this investigation just continues. And I wanted to finish with introductory slides by this reconstruction of the landing of Huygens. And this animation is based on real data, which has been recently reanalyzed and put together to this animated landing. So the motion of the probe when it touched down is the most accurate representation of all data of the accelerometers, of the visual images that we have. So I will leave this moving and we'll go to the next speaker.
Yes, very interesting. I would like to watch. Anyway, yes, good afternoon. And I will describe some of the results that Cassini achieved about the interior structure of Titan and the smaller moons of the Saturnian system. Of course, the interior structure is very important because it determines the bulk composition of those bodies. The bulk composition is crucial for understanding the formation processes and the thermal histories of these bodies. The interior tells a story which is quite different, or maybe quite different and complementary to the one told by other remote sensing instruments. Of course, so far planetary exploration focused mostly on surfaces because they are easily achievable. We don't have many tools for understanding the interior structure of those bodies. And among these tools, we have to list, of course, magnetic fields, gravity, altimetry, and rotational state. In the case of the Saturnian moons, unfortunately, magnetic fields don't tell us much, as they say, for example, in the case of the Jovian moons, because Saturn has this characteristic of having a magnetic field which is really almost aligned to the rotation axis. So we cannot infer, for example, the existence of subsurface oceans from magnetic measurements that it was done by Galileo at Jupiter. I will describe mostly what we obtained for gravity. Gravity focuses on two main issues. The static gravity field, which tells us about the bulk composition, the moment of inertia, how mass is distributed inside these bodies, and also tides, the variable part, which tells us about the deformability of the body. And one of the important results that we obtained at Titan was using 6 gravity flybys devoted to gravity. And in this case, the high-gain antenna has to point to ground, because we are measuring the gravity field by measuring the tiny accelerations that the spacecraft suffers when it flies by a satellite. And we have sensitivities of the order of 10 microns per second, just to give you an idea. Well, when we flew by Titan 6 times, we have been able to detect changes in the gravity field. And these changes in the gravity field cannot be attributed to any other thing than tides. We have determined that Titan is highly deformable at orbital frequencies, and this means that under the surface there must exist a liquid layer which allows this deformation, this pumping up and down of the surface. How big are these tides? About 10 meters if we look at the physical displacement of the surface. In terms of however, deformation in the gravitational field, we are at about a few percent of the elliptical part of the field. So this was an important result that told us that under the surface there must be a liquid layer. Where the Titan, a completely rigid body, the deformation would have been only 1 meter. But remember, we didn't measure directly the physical deformation of the body. We measured the effect of the deformation on the gravity field. It's much easier to measure. This was an important result with implications also about the atmosphere, because the ocean can act as a reservoir of the methane that is found in the atmosphere of Titan. The measurements, unfortunately, don't tell us anything about the depth of the ocean. Could be only 100 meters in principle. Probably is a couple of 100 kilometers according to the most established models. And how deep is buried this ocean? Well, we don't really know, but recent measurements tend to indicate that the crust of Titan is relatively thick and rigid. So probably the ocean, according to this gravity topography correlation, turns out to be about 200 kilometers. Another important result that we obtained recently has to do with another moon, which is Enceladus. We have been able to determine the asymmetry in the gravity field between the two hemispheres. And this asymmetry told us something very important about a possible liquid reservoir which exists under the surface of the South Pole. Essentially what we did was to measure a gravity anomaly, a negative gravity anomaly at the South Pole. We knew already from images that the South Pole was deformed and there was a large depression. However, the anomaly that we measured was significantly smaller than expected, and so we have been able to infer the existence of this extensive and large water reservoir about the size of Lake Superior, just to give you an idea, at about 40 kilometers deep depth under the surface. So this was an important result. I would like to conclude, however, with a remark that all these measurements were not foreseen in the prime mission. And they were made possible only because of mission extension. Where the mission not been extended by NASA, all this would have been completely lost. And now, of course, we are looking to other measurements, both at Enceladus and the other moons, and possibly with future missions. Athena?
Mm-hmm. Yes, good. So, great, Luciano. So, Luciano mentioned the presence of subsurface liquid water reservoirs in some of these moons around Saturn, and this has been a huge revelation for scientists. I wanted to start by saying a mission like this is a unique opportunity in a scientist's lifetime. I was very lucky after I finished my PhD, which happened to be on Titan Voyager data, to run immediately into the preparation of the Cassini mission. That was a long time ago, but we started working on this in the early 90s. And it's fantastic to get a chance to be participating in writing the proposals for the instrument, the definition, the description of the instruments, and the scientific objectives. And it was just a fantastic experience for me that I'm still living today, thanks to the fact that we have the extended mission. So I fell in love with Titan in the beginning. That was my PhD, and Titan led me very naturally to the consideration of the habitability issues in our solar system. Everybody's looking for life in the solar system. Every time I give a conference, they say, well, have you found life yet? Say, well, maybe in the exoplanets one of these days. In the solar system, we're still looking, but before finding life, one should look for habitability conditions. And the habitability conditions are 4 requirements that you see there. You have to have, for life at least as we see it on Earth, water, liquid water, the essential elements, the nutrients, the food, basically. You have to have some energy to get the system to work. And the system has to be in a stable environment. You cannot find yourself in binary, star systems and things like that. They disrupt everything. So the habitability zone is a notion we've had for quite some time now, in which this is the region where a habitat, a place where life could emerge or life could be supported, exists in our solar system. And here you see our sun in the middle in yellow, other types of stars around it. And the habitability zone in our solar system used to be that light blue line that you see here for surface habitats. And as we said in the beginning, and as Luciano just said, everybody was looking at the surface at the beginning to see if you could find liquid water. Nowadays, thanks to discoveries and measurements that we have that show that liquid water could exist underneath the surface of some of these bodies, the habitable zone has gone all the way to the outer solar system. Just imagine you're looking at Enceladus, this tiny little moon, and it's erupting. It's spouting this water vapor out in space. It's only 500 kilometers wide, and there is water vapor coming out of the south polar region. That was the first hint that told us, no, stop looking for surface habitats. You've got what we call deep habitats now. These are the moons around the giant planets. There they are, several of them. We've had a chance to look at the Jupiter moons with the Galileo mission back in 1995. We have the JUICE mission now planned to return to the Jupiter system and look at Ganymede, Europa, and Callisto. And for Saturn, we had the wonderful opportunity with Cassini. And Cassini has shown us a number of things that you can see in the next slide, which shows you how Titan and Enceladus were both revealed to us. Titan's surface was something that we had never imagined. The first time I saw the Titan image coming down at Darmstadt, the control center for the European Space Agency, I said, would someone please remove this Mars image from the screen? Because we're really waiting for Titan. It was pebbles sitting on this brown, riverbed. It looked so much like Mars. But not everything looks like Mars. Look at all these sites there. You've got mountains, you've got dunes, you've got lakes and channels. None of us in our wildest dreams, not even Ralph Lauren, and he's got a wild imagination, could have imagined anything like that popping up. And Enceladus, those geysers in the southern pole, this is something we cannot observe from the ground. You need a mission to go there and look at this. So it's a fantastic way to explore the Saturnian system and to look at things that are actually quite close to our own planet. If you want to find out about climate, about the evolution of climate, here you have a tiny little moon that has organic chemistry in its atmosphere. the combination of the nitrogen in the atmosphere, where you're breathing right now, sitting here, the air you breathe is nitrogen. People say, when I do the conference, say oxygen. No, you're breathing nitrogen, 78%. All right, so the same thing on Titan. Then you have the organic chemistry. You have the climate evolution. You can learn things about the emergence of life and the climate evolution that concern our planet also. And in the case of Enceladus, you can also get information on the habitable conditions in the solar system. So for me, all the instruments work together. My favorite instruments are infrared spectrometers, because I do a lot of spectroscopy and I try to find out what's the chemical composition in these bodies and what's the temperature like. I also look at the surfaces with spectroimaging data. And I think this mission has brought to us, I think, almost every day, a new discovery, a new image, a new fantastic thing that we can dig our teeth in and find out a lot of new things about our own planet and the emergence of life and the habitable conditions. So in the future, my dream is to go to back, because we all want to go back with a mission. And so I hope that sometime in the near future we'll be able to go back and do another mission to Titan or to Saturn. Thank you.
Well, these are hard acts to follow from what we've heard, and I have to move you away to more abstract things. Unlike Athena, I didn't do my PhD on Voyager. I actually was a principal investigator, I still am, when I started my career many, many years ago. And so I'm grateful to be alive to watch this wonderful evolution, both on Voyager, but more importantly on Cassini, and participate with all these young folk on all the discoveries that are happening on my left and my right here. You might wonder, what is magnetospheric imaging? And what does that mean? How do you image electrons and ions? And that I will show you some of that later on. But this mission is the first and only planetary mission to carry this kind of an instrument, and we have learned all kinds of wonderful things. But let's start from something more mundane, and that is Van Allen belts that some of you they may have heard of in your education at the university. We have Van Allen belts at Earth. It was the beginning of our space age. And the first question is, does Saturn have Van Allen belts? And sure enough, it does. And this is a schematic view of the intensity of the Van Allen belts at Saturn, except that in the case of Saturn, they're essentially sculpted is what I use the word for, to say that the moons actually absorb a lot of radiation in the Van Allen belts of Saturn, and they create big holes. Mostly it's the Mimas and Enceladus and Tethys. So what does then mean? Does that mean about the magnetosphere per se? In the next slide, what you will see is that the Moon Enceladus, for example, that you've heard now, that it contains a pretty substantial lake on the South Pole, or ocean, as the case may be. And what is depicted here is magnetic field connections between Enceladus and its jets and the upper atmosphere and ionosphere of Saturn. And this is a schematic that was published a couple of years ago. And what you can see is that there is material that both moves out of Saturn's atmosphere and into Enceladus, and also from Enceladus into Saturn's atmosphere, and kind of essentially zaps it with millions of amperes of current. So, and we have the capability with this particular instrument that I talked about, where we can actually separate what comes out of Enceladus and also what comes out of the upper atmosphere of Saturn. And what we found is that there is a lot of hydrogen, but with 3 atoms put together, H3, and charged. And therefore, we know that this material comes out of Saturn. So okay, now as we move farther, much farther from the planet into the magnetosphere, this is what I was talking about. What you see is the north hemisphere of Saturn, and you see these white stripes that are the aurora, measured by the UV instrument. And then what you will see, hopefully, is a movie with sound of, these are radio waves from Saturn that are consistent with this explosion that took place that you might have seen. I don't know if we can play it again, Nico, but you see the radio waves, and then you see this big explosion on the back. And that is what you might call the equivalent of a magnetospheric hurricane. And I think I can use that word because you're talking about power that is of the order of 200 gigawatts to 200 trillion watts. So that is 1 gigawatt, remember, on Earth is a pretty large power plant. And we're talking about explosions at Saturn, which I would call a magnetospheric hurricane that happens on a daily basis and liberates that much power. So that is the active part. The other thing that we have a problem with, if you like, is that we're trying to measure the period of Saturn. How long does it take to rotate around itself? And it's about 10.7 or 10.8 hours, give or take. And we found out that it's different in the southern hemisphere than it is in the northern hemisphere. And we know darn well that Saturn rotates as a whole body, not differently in the northern hemisphere and in the southern hemisphere. And as the change in the seasons took place that Nico told us about as we moved into a different phase of the season, then we found out that the two merged. But we still don't know what the actual rotation period is. And in fact, the electrons and the ions move together with that. So with that, I'd like to show you the final slide, which is essentially a database 3D concept of the magnetosphere. And the dimensions, by the way, what you're looking at from the front to the back is like 12 million kilometers. It is not a small object that is influenced by Saturn and its magnetic field. The red part around Saturn in the center, and all of this is to scale, is the ring current, which is also connected to the north and south aurora that I talked about. And you could see the actual connection taking place when you had these big explosions. And the big explosions are on the night side. If you can click, I want to say something. If you click one more, just go on. There are a couple of animations. And it shows the tilt of the current seed on the night side, which is very different from the width of it, which is very wide on the day side. And then you have to realize, and if you click again, that there is all this water plasma that is ionized and circulates around the planet, close to the period of the planet, and some of it, as you see, jumps out into the solar wind. And the amount of energy that represents is like 20 to 40 gigawatts that come out of the magnetosphere and into the solar wind. So, Saturn is an impressive place. And unlike what my colleagues were saying earlier, doesn't quite stay still. Things are happening all the time, and with the new technology that Cassini has carried with it, it has been possible to really look at this and document it, and we look every day at the data and wonder what's going to come up next. Thank you.
Okay, well, I got my start all the way back on Voyager. I was actually there for the Voyager launch and wrote my thesis on Saturn's rings using Voyager data.
She's a lot younger.
So it's wonderful to get an opportunity to work with Cassini. I've actually been with the mission over 25 years, and so it's been exciting to see it go from a concept after Voyager to grow into a mission and to have now celebration of a 10-year anniversary. So I'm just going to hit a couple of the highlights and then show a video at the end of what's next with Cassini. So the next slide, please. This is showing Saturn as we saw it when we first arrived in the system. You can see the rings, and what you're seeing is the northern hemisphere of Saturn. It's winter, and Saturn looks very, very blue. It turns out that that golden color is only in the lit hemisphere, or the hemisphere that has spring or summer. And if you go forward a little bit, what we're seeing today is that blue color has changed. In the next slide, you can see just a hint of it in the northern hemisphere, and now as we move into northern spring and summer, you can see the south is starting to turn blue. So this was a surprise to see that. And if you go on to the next slide, we can actually see the little bit of that color is left at the very at the north pole of Saturn, and that's inside a hexagonal shaped jet stream. It's six-sided. It's been there since Voyager, and in the very center of the hexagon is a hurricane. You could basically pretty much fit Europe inside of that hurricane. You have speeds of about 150 meters per second inside of it. And that greenish color inside the hexagon is because there are still small haze particles. The sun hasn't been shining for that long at the North Pole. And as the haze particles grow larger, they'll basically cover it with that golden hue once again. Moving on to the next slide. If we jump to the rings, there very recently a paper was published about a bright feature that was discovered at the edge of the ring. What you're seeing there inside of the small square is the edge of the A-ring that's blown up. You can see that bright feature. If you go to the next slide, that bright feature appears to be associated with the birth of a small icy moon that's forming inside the edge of the A-ring. The object got the nickname of Peggy. It turns out that Carl Murray, the discoverer, it was his mother-in-law's 80th birthday, and so he nicknamed this object that he saw after her. That little tiny moon is only about 2 kilometers across. You're not actually seeing a picture of the moon, but instead the disturbance that it makes at the edge of the A-ring. You can imagine throwing a pebble in a pond, and as those ripples spread out, in the same way you're getting structure, or you're getting a feature at the edge of the A-ring. That feature is about 1,200 kilometers long. If you go back, Nico, about 1,200 kilometers long, about 10 kilometers wide. What's so key here is we think that these kinds of objects that form are similar to what might happen inside of a dusty disk from which planets might form. So this helps us understand planets forming in our own solar system and perhaps around exoplanets as well. And if you go to the next slide, Nico, what we can see here, this is with the sun shining edge onto the rings. Anything that sticks up above or below the 10-meter thick rings casts shadows. In that blow up, that larger square, you can see 2 tiny objects casting shadows. And those shadows are about 0.5 kilometer in radius. And if you look carefully in that image, you see that they're little boulders, basically, or what we call proto-Peggies, inside the outer edge of the A-ring. And from these, it might be a stellar nursery from which moonlets are born that then leave the rings and go on to perhaps come together and perhaps have formed the larger moons in the Saturn system. With the next slide, just to conclude, what I want to show here, what's coming up in the final 4 years for Cassini. What you see in those panels is just each of the 4 years we have left. The top line is the number of orbits, ranging anywhere from 12 to 56 orbits around Saturn in that very final year. Each of those little tiny Titans tell you about the number of Titan flybys, anywhere from 12 to 6 flybys in the final year. We have 3 more close flybys of Enceladus, 1 more through the plumes to sample the plume and make measurements, see if there have been any changes with time, and then some close flybys of some other icy satellites in the system. And if you click again, Nico, what we're there to explore new seasons at Saturn. We haven't had a spacecraft there to look at the spring and summer. We're going to be there until northern summer solstice. With the next time step, look for waves on Titan. We think the winds will pick up and there might be waves on those seas and oceans of liquid methane. And we're going to measure the depth of the largest sea for Enceladus to sample the plume emissions and look at the North Polar region. Going on to the next one, the rings, the best lighting angle ever on the rings with the sun very high shining down on them. Finally, these end-of-mission orbits, 22 orbits where we dive between the ring and the planet. And then finally, it would take another 30 years, that's the orbital period of Saturn, if you had to wait to come back for the summer season. And with the next slide, I'm going to show a video. This would be for the next 3 years of Cassini the movie. Here's what we'll see.
Cassini is there in the Saturn system now, has been making discoveries for the last several years, and there's more to come. By studying the satellites in the Saturnian system, we begin to understand something also about the origin of the solar system.
There is strong evidence now that most of the surface of Titan is in fact covered with organic material of some kind.
We're going to be looking at lakes on the surface of this moon in detail. We're going to be looking at the atmosphere to see how the climate changes over time.
We have some global circulation models that tell us as the winds pick up, we think there could be waves on the lakes of liquid methane.
Can you imagine anybody thinking that we would discover active cryovolcanism on one of these moons? Geysers? One of the things that we'll do in the next couple of years is make the first ever flyby through the plume when the plume output is at its maximum.
And then, of course, there's the planet Saturn itself. As we go through our series of orbits and as the seasons change, it's like having a brand new mission.
One Saturn year is nearly 30 Earth years. To be there for nearly half of a Saturn year is a once-in-a-lifetime opportunity.
The sun now is coming up on the North Pole, so we're getting to see territory that was in darkness when we first arrived in 2004. Pretty soon we'll have the whole hexagon and the hurricane inside of it illuminated by the sun. And then, of course, the mission's end itself is completely unique.
Starting in 2016, ending in 2017, these orbits will take us up and over the north and south poles of the planet.
We're actually going to dive in between the innermost edge of the D-ring and the upper atmosphere of the planet itself.
From that, we're going to learn how is Saturn constructed from inside out.
We'll also get the magnetic field of the planet, the mass of the rings for the very first time, and get to sample a place that no spacecraft has ever flown before.
This is a mission that cannot be duplicated. So we really want to take advantage of this opportunity to observe seasonal variation in the system.
Stay tuned for northern summer.
Stay tuned for the film.
Thank you very much for the fascinating presentations. We'll now open the floor for questions, if there are any.
Thanks for that. Jonathan Amos. Linda, you've got to go through this beauty contest first, haven't you? Or you're in this beauty contest with the other missions. Can you just describe what the timeline is for that currently? I mean, one hopes they'll come out the other end in some form, but it's a hurdle you do have to get over, yeah?
Right, we're in the process with all of the missions that are an extension for NASA. I think there are about 7 of them. We've put in a senior review proposal. The next step is in May to go before a review board, and then in June, NASA will give the funding allocations to each of the missions.
Okay. That's good. Nicholas, the landing data that we have, is that still yielding stuff? I mean, I see you made that simulation. I haven't seen that simulation before. Is that really new?
Yes, that's new. It was made, I think, a year ago or a year and a half. It's based on a more careful analysis of all the data that you could have to produce this. But yeah, the data from Huygens are still being used, actually. There have been recent results by Ralph Lorenz, for example, showing the propagation of atmospheric waves in the atmosphere of Titan.
Schumann resonance has helped.
So yeah, also the existence of Schumann resonances that are actually consistent with the existence of the liquid water now discovered by the radio science team. So actually some data from Huygens, maybe at the beginning that you could not really put in context, are now starting to make even more sense with the detailed investigation of the orbiter.
And if I can just complement the temperature profile, the temperature pressure profile that the Huygens probe got from 1,600 kilometers, down to the surface is still used by all the orbiter instruments as the ground truth to calibrate the temperature profiles at different latitudes.
Thank you. Are there any further questions?
Sorry, this is a little bit unfair. I wonder if I could just ask a question of Tom in the back here, because I know you've studied this in the past. You gave a presentation on it as well a few years ago at EGU about what you could do in the outer planets for $1 billion. And I see that NASA has issued a call for ideas for Europa. And I just wondered, with your expert opinion, what you could buy for $1 billion.
You could buy a lot of radiation shielding, which you would need. That's the one thing that makes the Europa missions most difficult. There are two things. One is that it takes a lot of propulsive capability to get close to Europa and stay close to Europa. So you're looking at either a mission that spends a lot of money on propulsion and radiation shielding, or a mission that comes in and quickly flies by and then spends most of its time out of that main radiation belt.
But it is expensive to stay close.
Yes, yes.
What about other missions, he's asking? What other missions could you do?
You mean, he was asking
Europa, okay. Yeah.
But there are many other missions you could do for $1 billion. Exactly what you could do for $1 billion takes a lot of study, of course, to figure out. But we have lots of ideas for missions that you could fly for $1 billion.
Mm-hmm. Maybe less.
Are there any further questions? If there aren't, thank you all very much for coming. Mm-hmm. Thank you for the excellent presentations. And I'll hope to see you again tomorrow for a press conference on lightning in the lab and extrasolar objects. It's at 9 tomorrow. And because habitability was mentioned, I should also advertise another press conference on Thursday morning, precisely on that topic, at 11 a.m. Thank you. See you tomorrow.